Hi, today we're going to talk about standard reduction potentials, which are a really useful tool as we think about electrochemistry and its applications. So let's start out by talking about what electrical potential is, and it's really a sort of potential energy. So normally when we think about potential energy, we think about something like a rock sitting on top of a cliff, which has potential energy because it could fall at any time, which would create kinetic energy. So just where it's sitting positionally is what gives it its potential energy. Now, electrical potential is similar in that it's based on a charged particle's position in an electric field. So again, this is based on position, and if that particle changes position, that would turn that electrical potential energy into some other form of energy. The units of electrical potential are volts. Now, volts are what we call a derived unit, which means it's made up by doing operators on a couple of other units. Essentially, a joule per coulomb. So you probably recognize the unit of joule, which is an energy unit. Well, coulomb is a unit of charge. This is how much energy you have per unit of charge. You're also going to hear me referring to what we call a cell potential. Now, the cell potential is basically the maximum electrical potential that you could get out of an electric cell, like a galvanic cell. So far, galvanic cells are the only sorts we've talked about, but there are other sorts that are going to come up as we talk about electrochemistry. So let's now talk about a standard reduction potential. First of all, this is something that we measure. And when we measure it, we need to have a reference point. So as you're going to see on the next slide, the way we set it up is in reference to what we call a standard hydrogen electrode. In other words, we put the standard hydrogen electrode at 0 and measure everything else in comparison to that. Now, you'll remember that redox reactions occur in pairs of half reactions. And one of those half reactions is an oxidation reaction where something is losing an electron. And one of those half reactions is a reduction reaction in which something is gaining an electron. Now, if you look at a table of standard reduction potentials, as the name implies, these are things that are measured as reduction half reactions only. So what about oxidation reactions? Well, oxidation reactions are nothing but reduction reactions running in reverse, and we're going to take advantage of that. So if you want to figure out the standard reduction potential of something like the copper 2 plus being reduced to copper reaction, you would set things up so that the standard hydrogen electrode was your anode, because anode is where the oxidation happens, and then you set up the copper as your cathode, because the cathode is where your reduction happens. And then whatever the voltmeter read is what your standard reduction potential would be. So now I want you to do a little thought experiment. If you have a half reaction where the silver plus ion plus an electron turns into silver, the metal, and that half reaction has a standard reduction potential of plus 0.80 volts, what would happen if you had 2 silver plus ions plus 2 electrons, creating 2 atoms of silver metal? What would the standard reduction potential of that be? Surprisingly, the answer is also plus 0.80 volts. And this is something that people kind of struggle with. So let's look at an analogy. Let's look at 2 waterfalls here. And let's say that we were going to take both of these waterfalls and use them to build a hydroelectric plant. My question for you is, which of these 2 would generate more electricity? So on the right, we've got Niagara Falls, and on the left, we've got a fairly wide waterfall that is also only just 5 or 6 feet high. Which of those would generate more energy? Well, most people can readily see that Niagara Falls would win because the water is falling from a higher height and therefore has more potential energy. So let's now look at another pair of waterfalls. We're going to keep Niagara, but let's put in a waterfall that is falling from about the same height, but is slightly different. Which of these would generate more energy? The answer again is Niagara Falls. Why is that? The water there may be falling from approximately the same height, but one of those waterfalls has a lot more water going over it than the other one. And that is also important. So those are two important factors in terms of how energy is generated. And we can have an analogy to what's going on in our galvanic cell. We think about the height that water can fall when it's generating electricity, and that is equivalent to electrical potential. We can also think about how much water is falling over the waterfall, and that's equivalent to how many electrons are being transferred. So whether we're talking about one of a half reaction or multiples of the same half reaction, they're always still going to have the same standard reduction potential, because that is a measure of the height, quote unquote, that the electrons are, quote unquote, falling in order to generate energy. And that height does not change no matter how much water / electrons go over that waterfall. So let's actually look at standard reduction potentials and what they mean. You will see a large table in the back of your book that has a whole bunch of standard reduction potentials. So I've picked a few of them to show here. And you can see that we represent standard reduction potentials as E naught. The naught, of course, means under standard conditions. And so when you look at these values, the lower the value that you have for your E naught, first of all, the more likely a substance is to be oxidized. Remember that everything in this table is shown as a reduction reaction. And what this is saying is that substance is more likely to have the reverse reaction happen. The lower the E naught, the stronger a reducing agent that substance will be. Now, if you're confused by the term reducing agent, I highly recommend that you go back and review my introductory redox video. By contrast, if you have a really high value for E naught, you're much more likely to get a substance that wants to be reduced, and therefore that substance will be a strong oxidizing agent. In other words, it will like to grab electrons off of other things. So when we're calculating the cell potential for a galvanic cell or any other sort of electrochemical cell, we use this simple equation. Here is our standard cell potential, what we're calculating, and it's going to be equal to the standard reduction potential of our reduction reaction minus the standard reduction potential of our oxidation reaction. So when you find your standard reduction potentials from the table, you're going to plug them directly into this formula. Sometimes people will say, should I make my standard reduction potential of the oxidation reaction a negative? No, you shouldn't. So here's what we're going to do. When we look at a problem, the first thing we're going to do is we're going to write or find our balanced half reactions. And then we're going to find the E naught values for those half reactions on our table of standard reduction potentials. And then finally, we're going to plug those values into our equation. You'll notice I have a warning here. Do not change the signs on those standard reduction potentials. So let's try a couple problems. In the first one, we're going to calculate the E naught of the cell where we're taking gold metal, reacting it with fluorine gas, and producing gold ions and fluoride. So the first thing we need to do is to write or find our balanced half reaction. So here's our balanced equation. And what we do to find half reactions is we look for the same element on both sides of the reaction. So we have gold on one side and gold 3+ ions on the other side. That will give us one half reaction. And then we have two things that have fluorine in them. That will be our other half reaction. So let's take this first set of gold, and you'll notice we have two of everything. We want to simplify that down as much as possible because that's how it's going to appear in the table of standard reduction potentials. And also we need to make sure that we make it a balanced half reaction by adding electrons. So here we're going to have gold metal turning into gold 3+ plus 3 electrons. For fluorine, we have 3 fluorine gas turning into 6 fluorides, obviously those coefficients can be reduced as well. And so we can get F2 plus 2E minus turning into 2 fluorides. Now we're going to take those 2 half reactions that we just generated and we're going to find the values on the table. Now, if you look at the fluorine half reaction, we find that pretty quickly. If we look at the gold half reaction, we notice that what we have in our actual reaction is reversed from what we see in the table. And so what that tells us is our fluorine reaction is our reduction reaction. Our gold reaction is the oxidation reaction. So now we're going to take that information, we're going to plug it into our equation. Remember, the fluorine is our reduction reaction, so that's going to be 2.87 minus our oxidation reaction 1.42, and that ends up being 1.45 volts. And again, people might ask, why don't we make that 1.42 a negative 1.42? Well, remember that our equation is already subtracting our E naught for the reduction minus the E naught of the oxidation. That's where the minus comes in. A more visual way to look at it is this. Imagine that you have your cliff and you want to measure how far your water or, a rock or something is going to fall. So I've marked the elevations here, not with altitudes, but with voltages. So this is our electrical potential cliff. And you can see if we do 2.87 minus 1.42, that's this distance, and that is how far it's actually falling. The top elevation is where the fluorine is sitting. The bottom elevation is where the gold is sitting, and that's how we're doing this. If you do 2.87 minus negative 1.42, you'd be doing this whole thing, and that's not what we're looking at. What we want to see is what is the difference in electrical potential between the two reactions. Okay, so let's do another one, and I'm choosing this one because it is slightly harder than what we did before, in that we are not given a balanced reaction to work with. What we see is what's reacting with what. So let's go through and identify our pairs that we can use to write our balanced half reactions. Copper 0, copper metal, and copper 2 plus is our first pair. We can see that copper 0 is what's reacting with something, so that will go on the reactant side. And then we have iron 3 plus forming iron 2 plus. So copper forms copper 2 plus. That is not balanced because we don't have balanced charges, so we're going to add some electrons. That's what that will look like. Then our iron 3 plus, turning to iron 2 plus, that's also not balanced. We can do that by adding an electron. And now, let's find our E naught values on the table. Now, I've made it a little trickier here in that we have 2 iron half reactions and 2 copper half reactions. So you need to look carefully and pick the right one. And I'm not intentionally trying to confuse you so much as I just want to tell you there are going to be a lot more than 2 iron half reactions in the table. And there's also going to be more than 2 copper half reactions in the table. And sometimes it can get very, very confusing when there are multiple half reactions and you're just randomly looking for something that has copper in it. You have to make sure you pick the right one. Here's our copper 2 plus and copper half reaction. And you can see that what we have here is reversed. And then there's our iron 3 plus to iron 2 plus reaction, just as it's written. And so this is going to be our reduction reaction. The reversed one will be the oxidation reaction always. And now that we have located that on the table, let us plug those values into our equation. The reduction reaction goes first, 0.77, minus the oxidation reaction, 0.34. And that ends up being 0.43 volts. Now, something that's actually really important to know is, will this reaction be spontaneous? So I put an example of what that reaction might look like. Iron 3 plus is basically rust. So imagine that you have something rusty and you take a nice shiny copper penny and you stick it up against the rust and you put it all under water so things can go in solution. Will the copper penny start putting off copper ions? Will the iron 3 plus, the rust, turn into iron 2+ ions, which also go into solution? Well, generally we know by looking at our E0 value for the reaction, if that is greater than 0, it will be a spontaneous reaction. And this draws us into what we're going to talk about in our next video, which is how standard reduction potentials interact with free energy. So basically, standard reduction potentials are just one part of figuring out how much energy can come out of a cell. The other part we've hinted at is the number of electrons that move, and we are going to put those ideas together in our next video as we start talking about free energy and standard reduction potentials. I hope this was helpful, and I will see you again soon.